Solar energy. We're going to investigate a few kinds of solar energy and focus mostly on photovoltaic in this video. By intelligently designing our buildings, we can make good use of sunlight to heat our house in the winter and keep it warm, but not overheat it in the summer. This is called passive solar design. The difference between the summer sun and the winter sun is 47 degrees. So with proper glass and overhang, we can design our houses so the winter sun gets in and warms up a thermal mass, and the summer sun doesn't. This provides a living area that's naturally cool in the summer and warm in the winter, without any special technologies. You can also actively build structures to collect solar heat, such as this solar water heater that we're building in Guatemala. Concentrated solar power focuses the sunlight to one small area. In this case, these parabolic mirrors focus the sunlight to a thin pipe containing a fluid that ultimately turns a turbine and generates electricity. But one can also do other things with this concentrated sunlight, as we'll talk about later. And lastly, what most people think of when we talk about solar energy is photovoltaic cells, a technology that turns sunlight directly to electricity. There are 4 different kinds of photovoltaics that we'll address in this video. Please know them and be able to distinguish them. So maybe you've heard this statement: it takes more energy to make the photocells than they produce in their lifetime. In general, it takes about 1.5 years of using a photocell to produce as much energy as it took to create the photocell to begin with. And because photocells last 30 or 40 years, it's reasonable to say that we get 20 to 30 times as much energy out of a photocell as it took to make it. Now there's also a financial payback time. If you put solar cells on your house, it takes about 7 years to pay off the cost of putting them there. Is that competitive? Many investments double in about 7 years, so this is comparable to investing in stock. However, there are many people that would say that as soon as you invest in solar energy, you've already paid for the solar cells because the value of your house has risen by the same amount of money that you've invested. Please take some time and investigate this graph where on the x-axis we have the year, and on the y-axis we have the efficiency of photocells to turn sunlight into electricity. And you can see the different technologies. Here we have amorphous silicon, which is very popular. The efficiency isn't really high, but it's inexpensive. And we have your triple junction gallium arsenide here that has very high efficiency, but you could never afford to put them on your house. We might use them for spacecraft, or if we can concentrate sunlight. Here we have a new up-and-coming organic photovoltaics made essentially of different kinds of paint. Very, very inexpensive, but at present not very efficient yet. So what do we compare this to? How about photosynthesis? Because nature can turn sunlight into a usable energy form for us, but photosynthesis is very inefficient. The C4 plants, such as sugarcane and corn, have a higher efficiency, maybe 1%, but we can only use a small portion of what they produce. Additionally, if we use this to burn, we recognize that combustion is also very inefficient. So we think that solar cells could greatly improve over the efficiency of nature to turn sunlight into a usable energy form. Let's take a look at the increased rate of solar cell production over the years. On the x-axis, we have the year, and on the y-axis is a log axis now, in megawatts per year sold of photocells. And we see before the 70s, photocells were strictly for the space industry. They were very expensive, single crystal silicon. These were the ones that took more energy to manufacture than they produced in their lifetime. But it didn't matter because we really needed electricity out there in space, and we couldn't run an extension cord out to orbits. Then later in the 70s, the oil crisis slapped us in the face, and there was a great increase in the purchase of photocells for houses. The rate of production continued to increase for off-grid markets. These are houses that aren't connected to the grid, so they're going to be willing to spend the extra money to put photocells on their roof. And more recently, we have rooftop programs, but also big solar farms where we put large amounts of photocells in the desert, for instance, in the Carrizo Plain in San Luis Obispo. This graph shows the 3 different sectors for the use of photocells. So these are photocells that are connected to the grid, such as your house connected to the grid, or large solar farms. These are consumer products, such as a photocell for your cell phone. Although these consumer products are increasing in use, they're going down in percentage of the world photovoltaic market simply because the other ones are increasing so much faster. And the last one is off-grid, which is decreasing in percentage, again, because the on-grid purchasing is growing so much faster. Okay, so let's take a look at photovoltaic devices. We have polycrystalline silicon, amorphous silicon. There's also single crystal silicon that is very expensive. We don't use much anymore. And then different kinds of thin film technologies that are a growing portion of the market. So how does a photocell work? It's very much like the light-emitting diodes we talked about in the last chapter. You have your p-type doped silicon and your negative n-type doped silicon, or your p-n junction. And just like when we drove the electrons into the holes, they fell to a lower energy level and gave off light. If this junction receives light, it can pop an electron out of the lattice and promote it to a higher energy level, and we can drive the electrons backwards. So for instance, we have our p-n junction here, and for a small region called the depletion region, the electrons jump over the border and fall into holes. It's called the depletion region because there's no freely moving electric charges here, and so you can't conduct electricity. So if a photon comes in and bounces an electron free, that electron is not very mobile, and it may be much easier for it to move in this direction by pushing these electrons down a wire into the negative terminal. As a result, this terminal is positive, and this voltage difference can be used to drive an electric load. So this is your photocell. This can be used, for instance, to charge a battery. We can investigate these very interesting current versus photocell graphs if you like. Here's another that shows your maximum power is at this point. This is an energy graph here. This is increasing energy of an electron. And so here's a photon. It hits an electron and bounces it from a very low energy state to a very high energy state. We can collect this free electron and use it to drive our light, for instance. This is the voltage gap, or the usable voltage we have. It's much smaller than the energy that the photon gives off. Because of the nature of the semiconducting material, we only get this difference in voltage for the electron in the hole or out of the hole. However, you lose a lot of energy because your photon might be much greater in energy than this band gap. Also, we need to move the electrons through the band gap, and then we need to move them onto the wire, and that takes some voltage. So the usable voltage we get is always less than the energy of the photon that came in, and sometimes much less. If we design our band gap perfectly, we can get up to 32% from this single junction photovoltaic. Let me explain. This is the black body spectrum of the sun out in space, and this lower graph is what we receive at the Earth's surface. It's smaller because the atmosphere absorbs some of the sunlight, and in particular some of these infrared gaps by greenhouse gases. This infrared light corresponds to 1 volt of electricity, or 1 electron volt of energy for the electron. Over here in the visible we have 2 electron volts, and if we get a blue light, it can give an electron 3 electron volts if it hits it, or push an electron across 3 volts. And this graph shows the different energies for the different band gap materials we could make, like silicon, or germanium, cadmium sulfide, cadmium telluride, gallium arsenide. These all have different energies, and this graph shows the efficiency of this band gap to turn sunlight into electricity. So why is there a different efficiency? Well, because if we have a very high energy band gap material, only these photons will be able to promote the electrons, and all of these photons will go right through the material and you'll miss almost all the sunlight. Similarly, if we have a very low energy band gap material, then all of these photons will be able to promote an electron, but you'll only get 1 volt. And so these high energy photons, most of their energy will be lost because a 3 electron volt photon will only produce a 1 electron volt. So the single junction limit is 32% efficient. That would be if you have indium phosphorus at a band gap of 1¼ electron volts, you can get up to 32% efficiency. However, what if we had many junctions? So the sunlight comes in here and has to go through many different layers. And so we can look and see each layer has a different band gap energy. And so the very high energy photons will be absorbed and produce electricity. The lower energy photons will go through and interact with the deeper substance that have a lower energy. These photocells can be up to 41% efficient, but they're really, really expensive at $50,000 per square meter. The only use for these would be, again, out in space, where we need that electricity very badly. But on Earth, we can concentrate the sunlight, so we get a huge amount of sunlight onto this tiny photocell. And this way, the high efficiency pays for the extremely high price. Of course, these have to be actively cooled, because in one moment, the concentrated sunlight at about 1,000 or 2,000 times the strength of regular sunlight would immediately destroy them. You can make thin film photovoltaic solar cells by a number of different substances as you can layer them on top of each other to make this band gap material. It's a complicated process, but it can be very fast and very inexpensive. It's very much like a printing process where layer by layer you lay down these different materials. Nanosolar in 2006 became very famous for a rather high efficiency and inexpensive flexible thin film technology. Unfortunately, it made use of indium, which is very important for indium tin oxide, ITO, a substance that we find on our computer screens. We can see that as the demand rose with our increased use, the price increased by a factor of 10 over a 2-year period. Indium tin oxide is produced in a lot of different mines, and essentially we've run out of it. We're not able to mine it, produce it, at the rate the demand is growing. So conjugated polymers, this is the organic polymer photovoltaics that I spoke of before. It's very inexpensive. Essentially, you're just buying paint and you're laying it. It's very inexpensive, but still the efficiencies are rather low. They can be made flexible and in this sense very adaptable to different technologies. Here we see the decrease in the cost of production of solar cells as a function of the total amount of photocells produced up to that point in gigawatts. And so here the cost is in dollars per watt. Here is $2 per watt. So if you want a 100-watt photocell, it costs you $200 to produce it. Now we've busted through that limit and we're down to on the order of 50 cents per watt now. This is a very clear learning curve that shows an exponential decrease in cost of production as we learn how to make them more. This is very consistent with Moore's law. We remember Moore as the person who said back in the 50s, maybe it was the 60s, said every 18 months we're going to double the density of transistors on a computer chip and cut the cost in half. This law has held true decade after decade since, and there's every reason that the photocell industry should follow the same course of price decrease because photovoltaics is the same semiconductor industry as computers. And here we see First Solar, when they broke through the $1 a watt milestone, talks about how cheap they can make photovoltaics. However, what we see is if photovoltaics are free, the cost of photovoltaics on your house is still going to be significant. The greatest portion of the cost is retrofitting. If you put them in new houses, it's going to be less expensive, but still more expensive than the cell itself. That's why the most inexpensive way to generate electricity are these large solar farms in the desert that are creating so much controversy because they're environmentally impacting the desert. So there's many different ways we can use solar energy. We've just discussed photovoltaics.